In this video, we look at 3 more quadric surfaces, and they have these equations. So we're going to go through this list. I would just like you to notice the similarity between these 3 new quadric surfaces and the ellipsoid that we just looked at in the last video. Notice with the ellipsoid, you've got an x term and it's squared, you've got a y term squared and a z term squared. So all 3 variables are squared and we're adding. There's a plus sign in front of that, or it's positive, and then that one's positive, and then that one's positive. And then we have a 1 on the right hand side. And we saw in the last video that if we do that, we end up with an elliptical cross section in the in the YZ plane, and the XY plane, and in the XZ plane. And so together, these form an ellipsoid. So this is X, that's Z, and that's Y. And from the center, which is 0, 0, 0 in my picture, we're going to go plus and minus A units in the X direction. So we go from A to negative A. We're going plus and minus B units in the Y direction. That's negative B to B. And then Z goes from positive C down here to negative C. Okay, so that's the ellipsoid. Now, if I take that equation and I manipulate it just a little bit, just make one small change, the surface changes drastically. So notice this one looks almost identical to that one. The only difference is that's positive and that's positive. Well, that's the same. That one is negative, and that negative changes everything. This is called a hyperboloid of one sheet, and we'll see why that is when we look at the traces in the coordinate planes. Now, for simplicity, in this video, we're going to center our surfaces at x naught, y naught, z naught equals 0, 0, 0. Just to make it very simple to see the basic shape of a hyperboloid of one sheet, and this other type and this other type. In another video, I will show you how to take an equation that does not quite look like this and then complete the squares so that we can find out exactly what type of surface we have. This is called a hyperboloid of one sheet, not sheets. That shouldn't be there. And if you end up with 2 of your terms negative, and we've got an x term squared and a y term squared and a z term squared. So all 3 of them are squared, but 2 are negative and then 1 is positive. This turns out to be what's called a hyperboloid of 2 sheets. And that will make more sense as we look at the traces of this in the XY plane, the YZ plane, and the XZ plane. So it's going to be just like this, but with x naught, y naught, z naught equals 0, 0, 0. And then this one, which looks just like the hyperboloid of one sheet, except instead of a 1 on the right-hand side, it has a 0 on the right-hand side. This 0 makes it an elliptic cone. So we're going to look at each of these surfaces one by one, and we'll consider examples where they're centered at the origin. So here is a hyperboloid of one sheet. So let's say you've got x squared over 25 plus y squared over 9 minus z squared over 16 equals 1. And you want to know what this graph looks like. Well, one way that we can do that is we can look at the traces in the xy plane, the yz plane, and the xz plane. Basically, in order to find the traces, you're just going to set one variable equal to 0, and then you see what happens to, or see what the equation looks like. All of these traces are going to be conic sections for our quadric surfaces. So for simplicity, let's start with z. Let's make z equal 0. Well, then we've got x squared over 25 plus y squared over 9 equals 1. And I hope you recognize that from the last video. That's an ellipse. Both of these are positive. Both the x and the y are squared. I've got constants in the denominator, and I have a 1 on the right-hand side. So this is an ellipse, and it's centered at whatever we're subtracting from the x and the y. We're not subtracting anything from either of those, so it's centered at 0, 0. This is the trace in the xy plane, if I graph it. And I'm thinking of that as a point in the xy plane, not extending this to 3D yet. Now, to figure out how far we go in the x and y direction from our center, to find the endpoints of the major and minor axes on our ellipse, we look at these two numbers. We look at the 25 and the 9. It's convention to call the larger one of those a squared. So a squared is 25, and then you take the square root of that, and you get 5. Now, since the a squared, or the 5 squared, is under the x, you're going to go plus and minus 5 units from the center, which is 0, 0, in the x direction. Since it's under the x, we go in the x direction, plus and minus a units. So we're going to go 5 units to the right and 5 units to the left. Okay, similarly, my b squared, that's the other one. The smaller of those two numbers is called b squared. Take the square root of that, and we get 3. Since the b squared, that's 3 squared, it's under the y, we're going to go plus and minus 3 units in the y direction. So go up 3 and down 3. And these are points on our ellipse. So we're just going to connect those with a smooth curve. Easy breezy. All right. So that is the trace in the xy plane. Remember, the xy plane has equation z equals 0. Now, if I want to see the trace in the xz plane, I set y equal to 0 and see what happens. Now, if y is 0, this is gone, and I'm just left with the x squared over 25 minus z squared over 16 equals 1. Now, you might think that that looks like an ellipse, and it does, but that sign difference, that makes a huge difference in the shape of our graph. Since both of these are positive, we get an ellipse. But this one's positive and this one's negative, so it's not an ellipse, it's called a hyperbola. Now, when we're graphing this, we start in a very similar way to the way we were graphing the ellipse. First, you identify the center. We're not subtracting anything from the x or the z, so our center in the xz plane is xz equals 0, 0. And then we tend to think of the number in the denominator for this positive term as our a squared here. It doesn't actually matter which one is larger when it comes to hyperbolas. So we're going to call 25 a squared. Take the square root to get 5. Just like before, that tells us we're going to go plus and minus 5 units in the x direction, because this is x squared over 5 squared. Since it's under the x, we go 5 units, plus and minus 5 units in the x direction. So if this is z, I can draw my x-axis down here. X equals 0 is in the middle, so we're going to go 5 units this way and 5 units this way. Now, typically we would write our z-axis this way and our x-axis over here. But remember, we're about to go to 3D in a little bit. Here's our x, there's our z, and there's our y. Given that, I don't think I want to put my x-axis over here. I think I'd rather put it over here. So that way I can just imagine turning this 90 degrees so that the x-axis is coming out of the page. It's coming out at me like my thumb is coming out the camera right now. So I'm just going to turn this whole thing at a 90 degree angle so that I can see it in this perspective. So I'm putting the positive x-axis over here. So if I'm going plus and minus 5 units in the x direction, that's my plus 5 and that's my minus 5. That's the positive x-axis. And then we're going to do the same thing with our z. We've got this 16 under the z. We're going to call that b squared. Take the square root. Square root of 16 is 4. So we're going to go plus and minus 4 units since it's under the z squared in the z direction. So we go up 4 and down 4. And then we're going to make a little rectangular box. And this is different from the ellipse. Instead of just connecting those points, which is exactly what we would do if that was a plus sign, we're going to make a rectangular box. Little rectangle. And then draw lines through the on the diagonal of that box. This is an asymptote of our hyperbola. That's another asymptote of our hyperbola. Now, with hyperbolas, at least the right ones that we're going to be studying in this class, they're either going to open left and right or up and down. To figure out which one, we're going to do the same thing we did here. We're trying to get a sense of this surface, right? So we set y equal to 0. And then we said, well, then this is what it looks like. We're going to end up with this hyperbola over here. To get a sense of what this looks like, we can just pull the same trick, do the same thing. We can let one of these variables equal 0 and then see what point would be on the graph. So I'm going to let z equal 0. So when z equals 0 and I'm on this curve, I have x squared over 25 equals 1. And if I multiply both sides by 25, that gives me x squared equals 25. And if I take the square root of both sides, don't forget the plus or minus on the right, we get x equals plus or minus 5. So that means these 2 points x, z are on our graph. X equals negative 5, 0, and x equals positive 5, 0 are on the graph. So that point's there and that point's there, and that means our branches are the branches of our hyperbola. That's just those two pieces. They're going to look like this. Now you might say, well, how do I know that it's not on this axis? Well, let's see what would happen if we set the other variable equal to 0. Set x equal to 0 and see what happens. You've got negative z squared over 16 equals 1. And if you multiply both sides by negative 16, you get this. You've got z squared equals negative 16. Is that going to happen? Well, not in this class, it's not going to happen. If I take the square root of both sides, I get z equals plus or minus the square root of negative 16, which is plus or minus 4i. And although we love complex numbers and it's very interesting, we're not interested in those complex numbers in this class. So this never happens in the real number system. So what does that tell us? X never equals 0. So our graph never crosses this line, which is the z-axis in this picture is represented by x equals 0, that equation. Actually, we don't get any graph for any x between negative 5 and 5. We get the graph whenever x is greater than 5. We get a graph whenever x is less than negative 5. But any x in between, there's no graph here. So that is the trace in the xz plane. So now let's put these two pieces together. So far, I have a trace in the xy plane. We go plus and minus 3 units in the y direction, and plus and minus 5 units in the x direction. And so in the xy plane, we see something like this. We see that ellipse. And then in the xz plane, what you're going to see is a hyperbola that looks like this. I'm going to wait a little bit to draw it, but it's just going to come out like this and like this. So imagine it looks like this, but only in that plane. It looks like this picture, but in the xz plane. So it's going to be like that and like that on the side. And we'll get back to that when we see the other piece. Okay, so that was the xy plane when z equals 0. We've got the xz plane when y equals 0. The other possibility is that x could be 0. So if x is 0, then we're in the yz plane, and our equation is given by, let's see, we had x squared over 25 plus y squared over 9. I'm reading it through my paper. It's reflected. And then we had minus z squared over, let me see, 16. And that equals 0. Now if we're in the yz plane, x is 0, so this piece is gone, and that's our equation when we're in the yz plane. Notice I've got a positive and a negative, so that means we've got another hyperbola. Now one comment I should make before we look at that hyperbola is to look at this hyperbola here. Now we went through all of this just to prove to ourselves that our branches open left and right rather than up and down. So you can do this every time if you want to, but you don't have to. It turns out the reason this worked, when I set z equals to 0, I was able to solve for x. The reason I was able to solve for x was because that was the positive term. And the reason I wasn't able to solve for z here is because that was the negative term. So we'll see it, we notice a pattern. Whichever term is positive, the branches of our hyperbola are going to open on that axis. So this one is positive. It's got an x squared in it. So our branches open on the x-axis and not the other one. With that in mind, I notice the y squared is positive, so it's going to open on the y-axis. But we start this the same way that we start our ellipse problems. First, identify the center. We look at this. We say, what are we subtracting from the y and the z? Nothing. So, in the yz plane at least, the center is yz equals 0, 0. So I'm going to draw my z-axis up and down, my y-axis over here, and we're starting at 0, 0. Now, a squared, that's the 9. It's the one that goes with the positive term by convention. If I take the square root of that, I get a equals 3. So we're going to go plus and minus 3 units, because the 3 squared is under the y, plus or minus 3 units in the y direction, because this is y squared over 3 squared. So we're going to go 3 units this way, and 3 units this way. Now we've got the 16 under the z. We're going to call that b squared. B squared equals 16 if b equals the square root of 16. A and b are always positive. So we get b equals 4. Since it's under the z, we're going to go plus and minus 4 units from the center in the z direction. So go up 4 and down 4. And if I was graphing an ellipse, if this was a plus sign, I would just plot those 4 points and then draw a smooth curve, and that would be my ellipse. But since it's a minus, we don't draw the ellipse, we draw a rectangle. I don't know why I got in the habit of calling it a rectangular box. It's just a rectangle. It's 2D. Okay, so I've got my rectangle, and I'm going to draw diagonals through the rectangle. These lines are the asymptotes of our hyperbola. And the y is positive, so this opens in the y direction. And you could set z equal to 0. Oh, goodness. I can't believe I did that this whole time. It should not be a 0, that should be a 1. I'm so sorry, guys. If you were wondering why that was a 0, not a 1, that's an excellent question. I just wrote it down wrong. So anyway, back to what I was saying. If z equals 0, that's gone, and now I've got y squared over 9 equals 1. So y squared equals 9, so y equals plus or minus 3. That means these points, negative 3 and 3, when y equals negative 3 and 3, those 2 points are on our hyperbola. So the branches open left and right. Or you could just say the y is positive, so it's going to open on the y-axis, and you get this. Now we want to put all 3 of these pieces together. I've got something that opens on the y-axis and the yz plane. And then in a perpendicular plane, the xz plane, it opens on the x-axis. And then this is what it looks like in the xy plane. So we try to put all 3 of those pieces together. It's a little bit hard to see. It's going to look something like this. And I'm so sorry about the shape of this. I'm not very good at drawing this. It's hard. Say, what on earth is that, Miss Townsend? I don't know. That's a terrible picture. Let me draw it over here. This is the shape, basically. Its thinnest part is that middle part. It's in the xy plane. That's right there. It's kind of weird looking because it's of the angle that it's at. But we've got hyperbolas that open left and right and forward and backwards on either side of this. So you've got the one in the xz plane over there, the ones in the yz plane right there, and then the cross section parallel to the xy plane that turns out to be an ellipse. This is called a hyperboloid of one sheet. Now without these curves on it, I'm just going to draw it like this. If you've ever watched The Simpsons, it looks like the nuclear power plant in The Simpsons. Check that out. That's the general shape. That's the shape we're going for. This is a horrible, horrible picture. I'm so sorry. But if you check out the nuclear power plant in The Simpsons, you're going to see this shape. And this is called a hyperboloid. Whoops. Of one sheet. And notice the cross sections in 2 planes, in the y equals 0 plane and the x equals 0 plane, are hyperbolas that open like this. So we've got hyperbolas one way, hyperbolas another way, and then we've got ellipses parallel to the xy plane, or where z is equal to 0, or wherever z is equal to a constant. If we slice that way, we're going to have a bunch of ellipses. Okay, so that's hyperboloid of one sheet. And it looks just like this. If you've got 2 positives and a negative, the right-hand side is 1, or it can be made to be 1. If it's 10, we just divide everything by 10, so we get a 1 over here. And x, y, and z are all squared. So 3 variables squared, 2 positive, 1 negative, and a 1. That's a hyperboloid of one sheet. Okay, now let's look at the hyperboloid of 2 sheets. Let's do pretty much exactly the same equation. We'll change it a little. We've got x squared over 25 y squared over 9 and z squared over 16 equals 1. But rather than adding, and subtracting, let's make this negative and that positive. So that's going to give us a hyperboloid of 2 sheets. And you'll see why it's called a hyperboloid of 2 sheets in just a minute when we look at the traces. All right, so to find the traces, let's just set one variable equal to 0 and see what happens to our equation. So let's set z equal to 0 this time. If z is 0, that's gone. So we're just left with negative x squared over 25 minus y squared over 9 plus 0, so that's nothing, equals 1. Now if you want, you can factor out that negative sign. So it looks like this. And if you want, from there, you can multiply both sides by -1. It's cool. So now we've got x squared over 25 plus y squared over 9 equals -1. Now let's think about that. Does that ever happen with real numbers x and y? You're like, I'm not sure. Well, let's think about it. X squared over 25. X squared is always going to be positive except for when it's 0. So this is always positive except for when x equals 0, then we get 0. So it's positive or 0. This is also always positive or 0. If I add these two numbers together that are always positive or 0, am I ever going to get -1? I hope you said no, because you're absolutely right. This does not happen, not in the real number system. I'm going to say in R2, where x and y are both real numbers. This never happens in the reals, so that tells us, well, this graph doesn't cross the plane z equals 0. And remember, the z equals 0 is the xy plane. So the graph does not cross or intersect the xy plane. You look for a trace, you find nothing. There are no traces there. Okay, so that's the xy plane, and this is what we're looking for. Now let's set one of the other variables equal to 0 and see what happens. We set z equals 0. This time let's set x or y equals 0. So we'll set y equals 0. That means we are in the xz plane. So x is -25, we've got this negative x squared over 25. Y is 0, that's gone. And then we're adding z squared over 16. And that equals 1. I hope you see it. We've got a positive and a negative. That's a hyperbola. It's still a hyperbola centered at 0, 0. Here's my z, there's my, oops, it's because it's a right-handed coordinate system, like let's make that our positive x. So this is in the xz plane, our center is at 0, 0. Now we've got a 5 squared under the x. Let me write it this way. So I've got negative x squared over 5 squared plus z squared over 4 squared equals 1. We've got a 5 squared under the x. So we're going to go plus and minus 5 units in the x direction. We're going to go plus and minus 4 units in the z direction. And since it's a hyperbola, we're going to draw our little rectangular box. And then draw in our diagonals as the asymptotes of our hyperbola. Okay, so not much has changed there, but notice this time the x is negative and the z is positive. So when x is 0, we get z equals plus or minus 4, z squared equals 16. So that points on our graph and that points on our graph. So instead of opening left and right this time, the trace opens upward and downward. So that's what we see in the xy, or the xz plane. It doesn't cross the plane z equals 0. Let's see what happens in the third plane. We had z equals 0, y equals 0. Now let's let x equal 0. Remember, when x equals 0, we're in the yz plane. So if x equals 0, here's our equation. This guy is gone, and we're just left with that plus that equals 1. Hope you see another hyperbola. Here's the z-axis, there's the y-axis. I'm going to write that with our perfect squares in the denominator. So 9 is 3 squared. 16 is 4 squared. So we're going to go plus and minus 3 units in the y direction. We're going to go plus and minus 4 units in the z direction. You're always starting from the center, but in these examples our center is 0, 0. And then because it's a hyperbola, we draw our little box, little rectangle, and then draw diagonals through the box. Okay, we're here. Now if y equals 0, that's gone, and we get z squared equals 16 again. Or it's better off over here, multiply by 16. Z squared equals 16, so z equals plus or minus 4. The z is positive, so it opens on the positive or the positive and negative z-axis, opens on the z-axis rather than the y-axis. And that's what we've got. So this is what it looks like in the yz plane, and this is what it looks like in the xz plane, and it never crosses the xy plane. So if we put all these pieces together, you see why it's called a hyperboloid of 2 sheets. In the yz plane, it looks like this. In our picture, this one's crossing at 4 and negative 4. That's in the yz plane. And then in the xz plane, looks like that. So you put those two together, and you get something that looks like this. Now notice what our equation looked like. We had negative x squared over 25 minus y squared over 9 plus z squared over 16 equals 1. Notice that the positive term was the z squared, and it opened on the z-axis. That's going to be true no matter which of these 3 terms is the positive one. So if I had x squared over 25, or let's make that negative x squared over 25, plus y squared over 9 minus z squared over 16 equals 1. This one, it's going to look very similar to that one, but instead of, oops, I lost my glasses, just flung them across the room, excuse me. So instead of opening on the z-axis like these did, well, since the y is positive and I've got 2 negatives, and the x, the y, and z are squared, and I've got a 1 on this side. Since the y is positive and it has the form of a hyperboloid of 2 sheets, when x and z are 0, we're going to have y squared equals 9, or yeah, y squared over 9 equals 1, so y squared equals 9. So this is going to cross at 3 and negative 3. And instead of opening up and down, like this one with the positive z-axis, or the positive z, this one's going to open left and right, because the y is positive. And if the x were positive, we would see one of these little cups going over here in the positive x-axis, and then there would be one behind us in the positive y. So it does not have to open up and down like this. It opens up and down the hyperboloid of two sheets if the z is positive. If the y is positive, it looks like this. And if the x were positive and the other two were negative, it would open on the positive x-axis and the negative x-axis. So that's a hyperboloid of two sheets. All right. So we looked at this one. If I've got two positives and a negative, and the right-hand side is 1, or it can be made to be 1 so that we can write everything in this form, we have a hyperboloid of one sheet. I think of The Simpsons, I think of the nuclear power plant. It's got hyperbolas for cross-sections in two planes, and then if I slice in another plane, I get an ellipse. Now, if you've got two negatives and a positive, an x and a y and z are all squared, and a 1 on the right-hand side, you get a hyperboloid of two sheets. So you get two distinct pieces. Notice here the axis of symmetry corresponds to the term that was negative. Since the z was negative, it opened up and down. It opened around the z-axis. Over here, it's the opposite. Since the z is positive and the other two are negative, it opens on the z-axis. Now, you don't have to memorize all this stuff, although it's helpful if you have worked with it enough that you're comfortable with all these rules that I'm telling you. All this can go on your formula sheet. Now, you're not going to have enough time to teach yourself the material during the quiz, but yeah, if you put all of that on your formula sheet, it can just make you feel better when you take your quiz. You look at the formula sheet and it just makes you feel better. So I highly recommend that. And this last one, you can imagine what it looks like because it's called an elliptic cone. But we'll look at the traces in the xy plane, the yz plane, and the xz plane to prove to ourselves that it turns out to look like a cone. So I'll show you a picture of that in just a moment. But let's look at a specific example of an elliptic cone. Oh, need a new sheet of paper. All right, so let's say you've got x squared over 25 plus y squared over 9 minus z squared over 16 equals 0, not 1. This looks like a hyperboloid of one sheet. If that was a 1, it would be a hyperboloid of one sheet. But it's not a 1, it's a 0. If you see this 0, or maybe you see this equation rearranged, x squared over a squared plus y squared over b squared equals z squared over c squared. That might be on the other side. This represents what's called an elliptic cone. To figure out what's happening in all three planes, let's set a variable equal to 0 and see what we get. So in z equals 0, this guy is gone, and we're just left with x squared over 25 plus y squared over 9. That's minus 0 equals 0. Let's think about this. When does this happen? Well, this is positive except for when it's 0, and it's only 0 when x equals 0. And this is positive except for when it's 0, and it's only 0 when y equals 0. So if the sum of these two things that are always positive except for when they're 0 is 0, well then this has to be 0 and this has to be 0. That means we don't get a curve, we get a single point. One of my students said it's a degenerate ellipse. Kind of. We get 0, 0. You could also call it a degenerate circle. It's just a point, right? Just a point. There's only one point that satisfies that equation, and it's 0, 0. So if I'm looking at the trace of this surface in the plane where z equals 0, remember that that's the xy plane. So when we looked at our graphs in class, it's like the floor. Here's the x-axis, here's the y-axis, and there's the z-axis. We just get a single point. X and y are both 0, and z equals 0. So we're right there. That's the trace. That's all we get. Now let's see what happens if y equals 0. That would mean we're in the xz plane. If y equals 0, we get that. Now this looks a lot like a hyperbola, but it's not a hyperbola because we've got a 0 on the right-hand side. So it's not exactly the same, even though it looks like the hyperbola. It's that 0 makes it very different. Now at this point, we can do whatever we want to solve this equation. But since I'm interested in z as a function of x and y later, and we often are, I'd like to get z by itself. Just like you're used to getting y by itself in the xy plane, if we have z and x and y, we're going to get z by itself in terms of x or y. And it's just the way we tend to look at things in this class. Not always, but most of the time we do. So I'm getting z by itself, so I will add z squared over 16 to both sides. I'm going to multiply both sides by 16, so those guys are gone. This is my z-axis. Because we're in a right-handed coordinate system, instead of putting x over here, I'm going to put the positive x-axis over here. So we can imagine taking this like this. It's like my right hand, and I'm going to rotate it this way so that the x-axis is coming toward me. That's what that looks like in 3D. Okay. So this is my xz plane, and I've got this, and I'm still solving for z. So to get z by itself, I'm going to take the square root of both sides. Don't forget the plus or minus. So we get plus or minus 4 over 5 times x. So I had two equations. One is z equals positive 4 over 5 times x. So this goes through the origin, and then you go up 4 over 5. It goes through that point, and it looks like that. That's z equals 4 over 5 times x. Now the other one is z equals negative 4 over 5 times x. So instead of going up 4 and over 5, we want to go from here down 4 and over 5. So it looks like that. It's not exact, but I hope you get the idea. So in the xz plane, those lines are not looking very good, I'm sorry guys. In the xz plane, we'd see two lines that look like that. Now let's look at the last plane. We had z equals 0, y equals 0. Let's let x equals 0. So that's going to be the yz plane. So that's in the back over here. It's like parallel to my page. X equals 0, that one's gone, so we've got this. All right, not bad. So solve for z again. You're going to have two different lines, aren't you? Multiply by 16. You've got z squared equals 16y squared over 9. And you're trying to get z by itself. So take the square root of both sides. Don't forget the plus or minus on the right. So we get z equals positive or negative, square root of 16 is 4. Square root of y squared, it's going to be y. And square root of 9 in the denominator is 3. Okay, so we've got two lines. Z equals 4/3 of y and z equals negative 4/3 of y. So we're going to go up 4, rise over run, over 3. That's z equals positive 4/3 of y. And then we're going to go fall over run. We're going to fall 4 over 3. And that's z equals negative 4/3 of y. So this is the z-axis, this is the y-axis. You say, okay, how do you put those two together? We've got lines like this in the xz plane, lines like this in the xz plane, and it passes through the origin. Turns out that that's a cone. You guys believe me? The xz trace looks like this. There's part of it, and the other part of it's sort of behind us, like that. And then part of it goes through that axis, and then over here as well. And then the YZ trace, we could think of it as that line and that line right there. It doesn't have to be the scale, but I should see what we're seeing right here, which is a double napped cone. Okay, you say, okay, how do I know that that's a double napped cone? Because two of these are positive, one is negative. The x, the y, and the z are all squared, and the right hand side is 0. If it doesn't look exactly like this, but it can be rearranged so that it looks like this, you've got a double napped cone. Now, notice the axis of symmetry is the z-axis, and that corresponds to the negative here. So the variable in the term that negative is multiplying, that variable is the axis of symmetry for this. So if I have a negative z squared, I'm going to have an axis of symmetry on the z-axis, or if it's not centered at 0, 0, 0, it's going to be parallel to the z-axis. It's going to be on some vertical line, that's parallel to the z-axis. Okay, so just so that we have another example, let's say the y was negative instead. If I have x squared over 25 minus y squared over 9 minus plus z squared over 16 equals 0. Notice I've got all three variables squared, two positives, a negative, and a right-hand side of 0. Since the y is negative this time, the axis of symmetry is parallel to the y-axis. Since its center is 0, 0, 0, it actually is the y-axis. We're going to see a cone that looks like that. I wouldn't worry too much about the slopes here. Just think about this general shape. It's going to be a cone. And make sure that the axis of symmetry is correct, so that it's opening in the right directions. Okay, so those are our 4 quadric surfaces that all have x, y, and z squared in them. There's our double napped cone. If the x, y, and z are all squared, and the right-hand side is 1, and all of these terms are positive, we get an ellipsoid. And that ellipsoid comes from setting one of these variables equal, or one of these terms equal to 0. So we could say z equals z naught, now that's gone. And then we see an elliptical trace in that plane. And we set y equals 0, and we see a different elliptical trace. We set x equals 0, and we see a different elliptical trace. And when you put all those three pieces together, you get something that looks like this, like a football, some people say, or a peanut. I always think of peanut M&Ms, love peanut M&Ms. So yeah, you've got an ellipsoid, and this one is pictured with its center at the origin, but that center could be anywhere. It could be in any x naught, y naught, z naught, and you identify that from whatever you're subtracting from the x, the y, and the z. Okay, hyperboloid of one sheet looks almost identical. X, y, and z are all squared. Right-hand side is 1, but instead of having 3 terms that are positive, you've got 2 that are positive and one that's negative. And that leads to a hyperboloid of one sheet. The axis of symmetry is given by the variable of the term that's negative. So this is a negative z term, so it opens on the z-axis. Hyperboloid of two sheets looks the same. You got a 1 on the right-hand side. All three variables are squared, except this time, instead of having two positives and a negative, you've got two negatives and a positive. So you get two sheets. You can see why that's called one sheet, because it's just one piece, and that's called two sheets because it's two pieces. Now, if your equation looks like that of a hyperboloid of one sheet, positive, positive, negative, or actually even this one, negative, negative, positive would be fine as well, because you could multiply this one by -1 to get that one. If you've got two terms that have the same sign and one with the opposite sign, and the right-hand side is 0, or you can rearrange it so that the right-hand side is 0, but you have as a cone. This is an elliptic cone, and it opens in the direction of the axis whose variable is squared over here. It's really hard to say. Let's say it differently. I look at this term, or I look at these three terms. I see this one is negative. The one that's negative, if these two are positive and that one's negative, the cone opens in that direction. So this z is negative, so it opens on the z-axis. So that's our x-axis, that's our y-axis, and that's our z-axis. So these are the 4 types of quadric sections that have all three variables squared. Notice these 3 guys have 1s, the cone has a 0. The ellipsoid has all positives, and then if you've got some positives and negatives, you're in one of these cases. So that was a long video. Thanks for hanging in there. In the next video, we'll look at quadric surfaces where all the variables aren't squared.